Okay, so we're going to continue today with chapter 2, talking about atoms and the periodic table. And yes, it's not a full lecture. There's just a few slides and then mostly activities. Okay, so what we're going to do today, the objectives for today are that you're going to draw some Bohr diagrams. This is why we all have a handout. Please don't start yet. Then we're going to draw Lewis dot structures, also on this handout. And then I'll pass out these model sets, and you're going to explain, you should be able to, given any molecule in that model set, explain how many electrons are in the valence shell and how many electrons it can accept. So we'll pass out the models in a little bit, but not yet. So that's what we're going to do today. We have a short, it's short, so I think this is the perfect amount of stuff to do. Okay, so I have a 3-minute video because I think this guy can explain it with better illustrations in 3 minutes than I can explain it in 15. So.
Hi, I'm Josh, and this is the Science Classroom. In this video, we're going to talk about how to draw a Bohr diagram. Here's the kind of question you would need to solve for your chemistry class. Draw a Bohr diagram for silicon. A Bohr diagram is a representation of electrons around the nucleus of an atom. It's based on the Bohr model of the atom. The Bohr model isn't the best representation, but it can at least give an approximation of how many electrons are in the outermost energy level, known as the valence shell. First, we draw it in the nucleus. The nucleus is where the protons and neutrons are located. I'm going to include these amounts in the nucleus. Not all chemistry teachers will require this information, but I always recommend you add it here. Silicon has 14 protons. I know that because its atomic number is 14. It also has 14 neutrons. I know that because I round the atomic weight to the nearest whole number. This represents the number of protons and neutrons added together. It's called the mass number. So if I subtract the number of protons from this mass number, then I know the number of neutrons. Now I can show all the electrons. In the Bohr diagram, the electrons are drawn as little circles on a ring. Each ring can hold a certain maximum number of electrons. The first ring can hold 2, and then each ring after that can hold 8. So let's start drawing in the 14 electrons for silicon. Here's the first ring. It can hold 2 electrons. I'll draw them like this. Then I'll draw another ring. This holds 8. It's usually good practice to draw them in pairs like this. So I've drawn 10 electrons. There's just 4 left. So I'll draw in one more ring and place the last 4 dots on this ring. I'm going to space them out on all 4 sides like this. You don't technically have to do this spacing, but it's kind of the best practice to give symmetry for the diagram. Now to check our work, just count up all the dots. There's 14, and that matches the atomic number of silicon. Thanks for watching. If this video helped you out, please give it a like and subscribe to the channel. Hi, I'm Josh, and this is the Science Classroom.
We won't watch it again.
We're going to talk about how to draw a Bohr diagram.
Okay, so in summary, so what you're going to do on your handout. So everyone has a handout with 2 elements, and you're going to identify what element you have by looking at your periodic table. You're going to draw a circle around the symbol to symbolize the nucleus. Inside the nucleus, write the number of protons and the number of neutrons. And then determine, so you're going to determine which row your element is in. So whichever row your element is in is going to determine how many circles you have for your electron shell. And then draw the electrons on each shell. So the first level can have 2 electrons and all the other levels can have 8. Any questions about this assignment? We're going to do this for both. So you'll have 2 Bohr diagrams at the end. It's neutral. It's starting out neutral. So you're one slide ahead. Okay. Which one? Okay,
Two can be on the first row.
This one. They'll have the same one? Strong hand. No, it should be. Oh, sorry, it should be this one. Is it on the left side of the paper? It should be SR, my bad.
Only to show you plus two.
Same number of electrons. Yeah. I felt right.
Wait, so yeah, right?
Okay. Yeah, so there's a
that makes
couple
sense.
of rules. There's 3 rules that are really important. So, yeah. And I always see this line.
30.
So there's one of them on the
Okay, so
number of electrons.
yeah.
The number of
So in the fourth row, so there's the electron. You are smart. Well, count all the way across here. 4, 3, you did 2 plus 10 is 12, 30, 40. Yeah. Electrons.
4 times 8 is 30.
Issue is.
Oh, okay. So basically, 2 is 10. So 10 is 10, 30 minutes. You're gonna go. Yeah. Oh man, I made this. So we'll talk about that. Definitely more now. I'll mention it. You can put them, I think for now it's fine, yes, but there are 3 more on the. Yeah, we're only drawing the electrons right now. The Bohr model is here, so we call it Excel electrons. Okay. Hey, I got you. Yes, so there's one fact. I'm pretty sure I covered yeah.
So in the third row, he said fourth row. So that's just. Are you gonna talk about it?
Yes.
Yo, bro. Why did I get this? Why did I get this? I was right. So like, where are you?
So first row is for
Where's she at? She's in the fourth row. Here's the gun up. How many? So there's two people in each ring. Look at how many have it. The number of ledges. There's 2 atoms in the first row. But only 2 electrons.
Yes.
What element would be S?
Selenium.
Oh, sorry, okay, iodine. An iodine.
Yes.
18 on the third row.
One more. So lithium has
Yo,
an
can she,
it has 3 protons, 3 electrons. You only have 2, so you need 1 more circle. Yep. So like, so this first circle is very good. You need 1 more circle. Yeah, so draw 1 more circle and 1 electron. Yep. So like, so the circles are electrons. These little baby circles are electrons. You fill it in, so it's a dot. No, the protons are the number of electrons. Protons, electrons. So this one has a charge. These are ions. And these are pure elements. Oh, we're finding pure elements. And that's
Potassium, 2 in the first.
yeah, gotta draw 20.
Treasure 8 in the third, yes.
Yes.
And then 1 in the fourth. Yeah. Bohr model tends to break down.
If I should have gone, I meant to go, I meant, so my next slide has only the 3rd row.
Yeah, off-ball model would be better.
Okay, I shouldn't have gone that far. Yeah, I should have not done the selenium one. Or I shouldn't have done selenium.
Or anything with a T blocker.
I
Or
know.
the X blocker.
I got too far.
I fixed it.
I was trying to get 8.
You do that.
Yeah, but like, wouldn't it be like, for the second row, it'd be like 1 here, 1 here, 1 here, and then 1.
So basically, okay, so what happened? Yes. Okay, so because it gave you this right here and there's no plus chart, the charting. Okay, so there's 4 repeats. So we'll take a moment to like go around the room and find somebody else that has your same molecules and see if you have the same illustration. Yeah, you gotta talk to each other.
Whoa, you have like way more.
Oh, yeah. So I'll explain it. Yeah. Okay. This is my fault. This is a beautiful track. Beautiful first track. Yes. And yeah. I'll go over it.
What?
Yes. There's 10 more, so you can like 5 or you know 2.
Still like.
Okay, I will don't want to go ahead and sit down.
That's why he's DA. Getting a place like
Okay, let me okay, I'm gonna try to turn the video on here. And we'll go over. Okay. So I made a correction real fast. Okay, so I oversimplified, which is what happens when you like read the internet 5 minutes before you prepare a thing without thinking it all the way through. So if you go back a couple slides in the lecture, I have this image here, which has a few illustrations. And all of these have like less than 20 protons, which is probably where I probably should have stuck to things with 20 less protons, because those are the easy ones. But there are just so many of y'all, I got excited and made them too big. So we'll kind of, which is fun, y'all see the challenge. So if it had been too easy, you might not have learned anything. But because it was hard, and because I made a mistake, you get to learn from my mistakes. Woo! Okay, so the first orbital, this is right, the first orbital can hold 2 electrons. And so things with 2 electrons, which 2 elements have 1 or 2 electrons? Hydrogen and helium. So when we draw hydrogen, it has 1 electron shell, and it has 1 electron in that electron shell. Helium has 2 electrons, so when we draw helium, we add an electron. So these are too easy. I didn't give anybody these because these are really easy. So the very first electron shell, or orbital and shell are the same thing. It can hold 2. Now, when we go up, so when we go to lithium, lithium has 3 electrons. The first shell can't fit 3 electrons, so we draw 1 more shell. So, lithium, we had 1 more shell and 1 electron. So we're going to keep going across. Barium, it has 4. So we're slowly filling this in. If we go over to boron, it's going to have 3. And so what I was trying to get at, so if you look, so the number of rows, whatever row it's on, helium and hydrogen on the first row, lithium and beryllium are on the second row. So the number of rows corresponds to the number of outer electron shells. And the column tells you how many electrons are going to be in that outer shell. So lithium is in column 1. It had 1 electron in its outer shell. Beryllium has 2 electrons, column 2, 2 electrons in the outer shell. Boron, it's in the third. If we ignore this D block, we ignore that, it's in the 3rd column. So beryllium, boron will have 3 electrons in the outer shell. It's got 3 in the outer shell, 2 in the inner shell for a total of 5 electrons. Is that making sense so far? We just slowly keep adding. And then where did my eraser go? So the far one in that column, so neon, it has 10 electrons. It has 2 in the inner and 8 in the outer. Did anybody have neon? I didn't give anybody neon because nobody had the Farcom. So now both of these shells are full. This one has 2 electrons. This one has 8 electrons for a total of 10. So we go around to sodium. We're going to add a 3rd shell because it's in the 3rd row and add 1 proton. And the same thing, this one. So if we go all the way over to argon, argon can have 8 in its outer shell. AR, fun with words. Okay. So it's gonna get simple, and then it'll get hard, and I'll show you why. So after argon comes potassium. So potassium is in the 4th row. It's gonna have 4 electron shells. All those are full. It has 1 more out here. That's easy. After potassium is calcium, and it has 2 in its outer shell. This is the fun part though. So what's the 20 element? What's the 21 atomic number? SC? Say it one more time. Scandium. So here's what happens, and this is why these elements are in a different block. And let me go to a different slide. Let me find, I have one more slide that goes with this one really well. Okay, so this is where this comes into play. One reason why this chapter is so hard is because you need to know like things in different sections all at the same time. So this is saying 1, 2, 3, 4th. This is like our 4th shell. This is the S orbital. And then we go 4s, 4s, 3d. So what happens, what's weird when we get into these transition elements is now instead of putting their electrons in the outer shell where you would think they would go, because that's what you did for the other 3, they go in the 3rd orbital. So instead of adding, so it's called 3d because it's in the 1, 2, 3rd shell in the d orbital. So this one is going to have an extra electron in its 3rd shell, and it still has 2 in the outside. Yes. Yes.
So, one of the reasons why that happens is if you guys, so the third row, the 3rd shell can actually fit 18 electrons.
Yes.
You guys know where we get the number 18 from? How wide is the D block, guys? Can everyone count the D block on the periodic table? How many elements are in the D block? And by D block, I'm talking about that dark green section. Or orange on that periodic table. Well, the D block just itself. So look at the key on your periodic table. You see the D block? 10, right? Okay. So the weird thing about the D block is you actually can fill your D block at the 3rd energy shell. And I know that's kind of weird, like Dr. Harris was saying, like you'd expect the D block to start on the 4th ring. Okay, because you see the D block on the 4th row down. Mm-hmm. But it's kind of a weird thing about the periodic table, even though it's in the 4th row, those electrons actually fill in the 3rd ring.
Yes.
Okay, so the 3rd ring starts filling up to 18. You can actually get up to 18 electrons in the 3rd ring. You usually don't draw the Bohr model though past element 20 for that reason.
Yeah, my bad.
No, it's good for them to see, but usually it
breaks down.
The Bohr model kind of starts to break down for this reason, because it gets kind of weird, where you actually fill the 4s and then you go back and start filling the 3d again.
Yeah. So did anybody have gallium? Does anybody have gallium as a? Yes. Okay, so the proper way to draw gallium, and it's okay if yours did not look like this. So to get to gallium, we're going to put 10 electrons in this 3rd ring. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now there's 2 in the first shell, 8 in the second shell, 18 in the third shell. And now we're gonna go out to this outer shell. So now gallium is gonna have 3 in its fourth orbital. Cool. Does that make sense? Awesome. Okay. Did anybody have bromine? Did anybody have bromine as a? Yes. So bromine, you're gonna have the same thing. You've got 2 in the inner, 8 in the second, 18 in the third, and then 1, 2, 3, 4, 5, 6, 7 in the outer shell. So 1, 2, 3, 4, 5, 6, 7. So if you're in the P block, how many electrons you have in your outer shell is going to be like this row minus the D block. So this column. So 1, 2, 3, 4, 5, 6, 7. So you should have 7 in the outer ring. You should have 6 in the outer ring. 5, 4, and 3. Okay. So then, some of y'all had krypton as your favorite one. Krypton would fill this fourth ring. And then to get to SR, we're going to add 1 new shell. And it will have 2 electrons in it. Cool. Are there any even bigger elements? Did I make one more bigger? Did I make tellurium? So did anybody have to do TE? And nobody had TE? Whew, okay. Yes, question.
Would it be okay if we practice some just like
Some easier ones?
Yeah, so like we avoid the D block maybe.
Yeah, let's avoid the D block. So practice again
So
with.
could we give like?
I have a couple more.
Could everyone just choose like 2 to practice?
Yeah, you can flip your sheet across, like flip your sheet on the back.
And then they can compare.
Yeah, and pick any
Take a
2.
number off or something. I don't know.
Yeah, I like it. Any 2 from 1 through 20.
Iron do you want?
Iron bigger than 20. Let's say.
Oh, bigger than.
Choose an element calcium
Oh, the
that's smaller.
atomic number needs to be smaller.
Atomic number needs to be smaller than 20. Or you could say the way you're writing this, the number of electrons in the last line. Is these fill a ring lower or 18? It would be 18 in the row one in the ring underneath. I would, for iodine, there's going to be 18 here, and then there's going to be 2, 3, 4, 5, 6, 7 favorite shell, outer shell. I wouldn't spend any more time trying to period controls how many I would focus on trying to draw something
I like it. I forgot, I brought backpack.
Well, how many go in the first?
Yeah.
The draw. Two in the first ring. Yeah. So this is
Be smart.
okay. So how many go in second ring?
Yo, I agree. Yo, I agree.
Second ring. Well, why would you go that far? How many electrons do you have so far? 18, right? How many do you need in your fourth test? See that? How far over is that the fourth row? How many electrons are in the fourth
That was perfect. Carmen, beautiful. What's the report? Oh. I know, you can't count. Nice. Yeah, so we'll go with that on Friday. These are, they're called no gases. They're found, they don't form. All their electrons. What's the difference? And I honestly don't want to find so they're attracted to large. But they don't actually bond.
Mr. Vaughn.
They're they don't share electrons. One needs electrons, the other is negative charge. And they are attracted by electrons. And then if the covalent bond and the covalent bond they share electrons. So they're not charged, they share. Do you want me to?
That's Mr. Vaughn.
Because this is our, this is the these. This one is the even though it's called still only has 8.
So, if you're trying to find the most common element, you round to the nearest element.
Yeah.
Usually they'll tell you like that's where they ask you, but then they're like, this is magnesium, His mass is.
Oh my God.
Tell you that it's not really over.
I've seen it.
What is that? So what's part of
Oh, I know this big. Right there.
So you know not stop. You know that's all.
So you need 7.
So you do that, so you literally just subtract the protons from the mass.
Oh, it's 9. I thought it was 7.
No, it's 9, 2 in the inside.
You wanna check it out, Mr. Tom?
I
thought you were walking around. My bad.
Geniuses. Can you guys try aluminum just like really?
You want me to do aluminum for you? I got it.
Yo,
Yeah.
what's going on with potassium?
I thought you were about to have, 18.
Yes, but for potassium,
Yeah.
potassium fills its 4th S block, fills its 4th row before it starts adding to the 3rd. You literally read the periodic table like a book. So you say 2 in the 1st, 8 in the 2nd, 8 in the 3rd, 1 in the 4th.
Maybe I'll get it.
This is my favorite one for how that is illustrated. This one, it's still, even though it's in the 4th row, it's called the 3rd d orbital, so it goes in the 3rd orbital.
Yeah, and then you can put it up.
Okay.
Yeah, usually.
Yeah.
Use 1. Plus 3 rings. 3 over in the 3rd row.
Yes.
Over phosphorus. 1, 2, 3, 4, 5. That's why you your last row. If that's 2 plus phosphorus, I will like.
Charge. And probably, assuming 0 charge.
We're not gonna strike that down, but you might forget it, have it copied in your notes, put like a big colorful box around it. It's like,
There was so many. And this wasn't even.
yeah, so neutrons are in here.
And that's what everyone
It's a balanced atom.
I think it's a lot.
What if it doesn't matter?
Wait, are we saying?
Wait, no, it's gonna get even easier. Hold on, can I? No,
So we can just get you know what they
I would have to count.
That was
Oh, thank you. Okay. Does anybody have any questions about that?
Or if we did like. What am
Yes.
Yeah. Oh, the whole time.
Yeah, I feel like you did. I feel like you were like,
I think I have.
no, he probably
Wait, we also have sex on. Yes, all right. No, who cares? Stop. You're right. Wait, no.
It just starts off like.
It starts like.
Okay. So we've got like 10 more minutes. I kind of want to wrap up / show you an easier way to do this. So we started with the hard way, drawing circles and talking about the electrons in every single orbital, which was definitely the hard way to go. That's okay. We learn things the hard way sometimes. Okay. There is another way we can illustrate how many electrons that are in the outer orbital, which is called the Lewis dot structure. So the valence shell is the outermost orbital. So when we talk about the valence shell, we're only talking about the outside orbital and we're ignoring all the inside orbitals. And for this, we're going to ignore this D block here because they have a lot of shells in their inner levels, and they do some weird things, which is they're called transitional metals. So we're going to kind of ignore those for a while. If we just focus on the far left, those two columns, and these 6 columns here, and we take out the middle, we get this simplified periodic table. And this has 3 rows, and the row again corresponds to how many shells it has. And so hydrogen and helium only have 1 shell, so that 1 shell is their valence shell. Lithium through neon, they have 2, so their valence shell is the second shell, the second outer one. And the third, sodium through argon, have 3 shells, so their valence shell is the third one. And here we're ignoring all of their electrons in the inside shells, and we're just looking at how many electrons they have in their outermost shell. So the way you draw a Lewis dot structure for these, everything in the first column has 1 electron in its outer shell. So the way that we draw that is it's the symbol with 1 dot. So lithium does have 2 more electrons in hydrogen, but those are the inside shell. We're not counting those. Sodium does have 8 more electrons in lithium, but those are in inner shells. We're not counting them. So this is how we look at just what electrons are in the outer shell. Beryllium and magnesium both have 2 electrons in their outer shell. They're in the second column, so we're going to draw 2 dots. Boron and aluminum, they're in the third column, ignoring the D column, ignoring the D block. They have 3 electrons in their outer shell. Carbon and silicon have 4. Nitrogen and phosphorus have 5. Oxygen and sulfur have 8. Fluorine and chlorine have 9. Helium, neon, and argon. Helium has 2, because it can only have 2 in its outer shell. Neon and argon have 8. So you should be able to take all the elements that you've drawn, except ignoring the really, really gigantic ones that we looked at the beginning, but the ones that you just drew, you should be able to really quickly write its electron dot structure, its Lewis dot structure, by simply looking at the column in the periodic table. Does that make sense?
Yes.
Yay. Okay, so to get at, I don't want to throw too much more content, but a lot of you had this one question at the beginning, and the reason we draw these Lewis dot structures and the Bohr valence model is so you can understand how and why charged molecules appear. And this will also help you understand when we get into chapter 3 with ions, where these ions come from. So, did anybody draw lithium? Anybody draw lithium? Couple lithiums? Yay, one. Did anybody draw fluorine? Yeah. Okay, so everything on the periodic table has the same number of electrons as it does neutrons. So they have a 0 charge. It has as many so a charge, if the number of protons are equal to the number of electrons, the charge is 0. But so what happens is elements and molecules, they really like to have full electron shells, okay? So fluorine, it only has 7 electrons in its outer shell. It really wants 1 more. Lithium only has 1 electron in its outer shell. It doesn't really want 7 more to fill it up. It wants to get rid of 1, so its other shells are full. So what tends to happen is lithium will donate its outer electron to fluorine. And so if lithium donates an electron, if this electron migrates from over here to over here, this will now have a positive charge and this will have a negative charge. Because this guy will still have 3 protons, but he only has 2 electrons. And this guy will have 9 electrons and 9 protons and 10 electrons. So this is how you get the charges on your sheet that we did before. So they don't just like magically lose an electron. Some other element stole it from it. So anytime, in order to go away from this 0 net neutral charge, some element has to give its electron to someone else. And so elements in the first, second, and third column, they like to give away their electrons and become positively charged. So lithium frequently gives away 1 electron, it becomes +1. Calcium frequently gives away 2 electrons, it becomes +2. Aluminum will become +3 because it'll give away 3 electrons. Nitrogen likes to steal 3 electrons, become -3. Oxygen likes to steal 2 electrons, become -2. Chlorine likes to steal 1 electron and become -1. And so this is why we draw these dot structures. The reason why we're drawing these dot structures is because it gives you an insight into how many electrons an element either wants to have in addition to what it already has, or how many it wants to give away, so that they can have a maximum shell of electrons. Because that is kind of the driver between ionic chemical reactions, is that elements and the driver between chemical reactions is that elements want their outer shell full. Does anybody have questions about charge?
Why do they want their outer shells filled?
It's like, I want to say the words that come to mind are like equilibrium and symmetry and balance. It's more stable when it's full. Thank you. Knew I would get there eventually. An unfull shell is unstable. A full shell is stable. And so there's potential energy. When it's not full, there's a lot of potential energy there for reactions to occur. Any other questions? Okay, so I haven't had it on one slide. It has been on like multiple slides, but in my opinion, there are 3 rules. And so if you have them in one sheet, maybe that would help you when it comes to calculating how many electrons or how many neutrons a thing has.
You guys make sure you have this down somewhere.
Yeah.
There's still a lot of confusion. If you don't have that down, or you don't know how to calculate protons, neutrons, electrons, that's how you do it. You guys should write that down and like highlight it, make it rainbows and unicorns.
Rainbows and unicorns.
Okay, that's really important for you guys to know.
Does anybody want to read the first line? I kind of use shorthand. Anybody want to read the first line? Beautiful. And the second one? Awesome. And then the third one?
Start 0, the number of protons equals the number of electrons.
Awesome. So these 3 rules, given these 3 rules, you can fill out that blank table that I gave you on Monday. You're like, okay, but if there is a charge, that means that you either gave away or stole an electron. So that would be the only, if there's a charge, then this is not true. Cool. Any other questions? Awesome. Let's see. We drew that. I won't go to that. But so this is going back to the charge. This is one picture here. Sodium likes to give away its electrons to chloride, and that's how we get sodium chloride salt. So when it gives one electron away, we get a positive and a negative. But when we're looking at the periodic table, sodium is uncharged. When we look at the periodic table, chlorine is uncharged. It's only when they're brought together under the right conditions that they trade, that one gives its electron to the other and they become charged. Yeah, this is going to be what we talk about in all of chapter 3. So I told you this is a foundation. Beautiful. So on tomorrow, you'll work on some more you'll work on your assignments, finish those. And on Friday, we'll go in a little bit more to the periodic table. Yeah.
Will there be anything new assignments on Thursday?
No new assignments on Thursday. Yes, thank you.